Protein control. So we're very happy to have Sabyasachi Chatterjee from UIUC today. He has been at UIUC since 2017, and before which he was in Chicago and Yale. So he works on signal processing from a statistical point of view. Today, about cross validation.
Thanks, Piyush, for the invitation. I'm very happy to be able to speak here. Okay, so yeah, I'll talk about the theoretically tractable framework for K4 cross validation. So cross validation, broadly, you probably all know, it's a very general machine learning technique to choose tuning parameters. And if you see most analysis of ML algorithms, you will see the analysis assuming the ideal value of tuning parameter is chosen, but rarely you will see full analysis of the cross-validated algorithm, right? So that's kind of what motivates this work. This joint work with Anamitra Choudhury, who is a fifth-year PhD student in UIUC statistics, and this talk is based on our paper, available on archive. So here is the outline. So I'll first describe the setting, the problem setting, and a motivating question. And I'll then describe the proposed framework and the main result that comes along with this framework. And then I'll talk about some proof ideas behind this main result and then how to apply this proposed framework to some concrete estimators. And then I'll finish. So here is the setting. So I kind of a lot of my research is on signal processing from a statistics angle. So that's where I'll start. So that's the setting, simple setting of signal plus noise. You observe y, which is theta star plus epsilon. Theta star is the true signal. It could be a vector or a matrix. So it's 1D signal denoising or 2D signal denoising, or matrix denoising. And just to begin with, let me just say that we'll assume that the entries of the noise vector or matrix are IID from a mean zero sub-Gaussian sigma distribution. And we'll use this notation to mean the sub-Gaussian sequence model. So this, of course, you don't need sub-Gaussianity for the algorithms or the estimators that I've talked about to be applied. It's just for the theoretical results, I'll say, and you can probably extend this pretty easily to some exponential and more heavier things. So in this problem, without saying anything, there are n or n cross n parameters and n data or n cross n data. So the number of data points is same as number of parameters. So it's hard to say anything meaningful unless you know something more about the true signal. Right, and depending on the structure of the true signal that you are targeting, several fundamental signal processing or statistics ML methods can be used in this model. So like lasso or trend filtering or dyadic CART, which I'll talk about later, or if you in the matrix setting, singular null thresholding or nuclear non-polarization. All of these estimators, they can be used and they have a tuning parameter. Okay, so all of these estimators that I just mentioned, they are fundamental estimators, they have a tuning parameter. And so you will see that there exists, so I'm interested in mean squared error bounds for these types of estimators. And you'll see that there exist mean squared error bounds for all of these estimators in the literature. But these estimators would again assume some kind of idealized value for the tuning parameter. And this theoretically recommended value would often depend on some unknown problem parameters, like the noise variance or something to do with the signal. So therefore, I mean, so in practice, people end up doing cross validation anyways, even if you know that it should scale some power of n sample size, but there's a sigma is Yes, typically, there's some unknown constants there. So you typically end up doing cross-validation. And as I was saying, so except for Lasso, there are a couple of recent papers. Such mean squared error bounds are unknown for all the other methods that I just mentioned. So it will be fair to say that a general and unifying framework to analyze sort of cross-validated versions of these kind of methods is lacking in the literature. That's kind of the point of this work. So let's start with an example method, which is fused lasso, where I have worked on a little bit. So the fused lasso is a 1D sort of vector denoising method, which is defined by this minimization of the square distance term to the data vector y, plus a penalty term, which there's a tuning factor lambda and a TV, where TV is basically defined to be the L1 norm of the consecutive differences of the signal. So this measures somehow the amount of variation in theta. So TV, the name stands for total variation. And if you think of theta as evaluations of a function, so you could also use this to do function estimation, say one-dimensional function estimation. And if you think of theta as evaluations of a function on a grid on 0, 1 with endpoints, then this TV theta is just a discrete approximation or Riemann approximation of the L1 norm of the derivative. So you're kind of parallelizing the L1 norm of the derivative. So here are some big sort of pictures. The green curve is the true function, let's say, and I've generated some points with noise. And so if you choose tuning parameter differently, of course, you'll get different fits. And you can see, for example, here we are overfitting. We've chosen lambda pretty low, and here we are kind of sort of over smoothing the data. And this is sort of the right value of lambda, let's say. So typically that's the case, right? In these problems, that you have a sweet spot of the tuning parameter, which is going to be good, and typically that's found by some sort of cross-validation. So let me give some examples. The results are not very important for this talk, but I just wanted to give an example of the kind of, I was talking about results existing in the literature. So for fused lasso in particular, there are some interesting results. For example, if you choose your tuning parameter in a certain way, then you have this cube root kind of rate guarantee on the mean squared error. Okay, so it depends on the true total variation of the signal, the 1/3 and this n to the -2/3. That's kind of known. So that's, you can think that this is consistent for any function of bounded variation. There's another sort of type of rate, interestingly. So if the true function, instead of the smooth function, it's a piecewise constant function, then it's known that you can actually attain a faster rate than n to the -2/3. In fact, a parametric kind of rate, where k is the number of pieces of the true signal. So instead of this green curve where it's kind of smooth, if I had a green curve which was piecewise constant, you would get a much better fit with less sample size. Okay, so the rate is much faster, but you have to choose your tuning parameter in this particular way. So again, you can see. So the point is, you can see that the ideal choices of lambda depend on sigma. They depend on k in this case, the number of pieces which you don't know. That's a property of the true signal, and this c is also mostly unspecified. So you see that the optimal choice of lambda depends heavily on the unknown true signal, and this is kind of the status for other methods as well. So that kind of motivated this question. So I was working on fused lasso.
So depending on how you penalize your theta, optimal theta changes. Is that right?
No. The optimal theta star is the same. You don't know what it is. It could be.
This was the last slide, so I have to make sure I get this right. Before this, sorry.
Yeah. So this theta is the variable, the optimization variable. So that's nothing to do with the true theta.
The true theta which generates all the values.
I'm calling it theta star.
Right.
So that's what generates the data.
Yeah.
And so that's the green curve.
Sure. But in optimization, if I generate data from theta star, and I have some arbitrary lambda, how do I ensure that the argument is achieved by theta star?
Here y will be generated from theta star. So that's theta star plus epsilon. So of course, theta hat is a random variable because there's epsilon here. So you're interested in how the random variable converges to theta star, or how close it is.
I think so you're saying your claim is the theta hat will still converge to theta star, even though you have this TV theta over there, it won't converge to anything else. Okay, yeah.
Because in case theta star has bound, small total variation. So there was the total variation also inside the rate. So of course it will be bad if the total variation is big. Right? So you're targeting signals which don't vary too much. So yeah. Otherwise, yeah. So
because the theta star also changes, I guess, right? It's true theta star. Now.
Yeah, you don't know the true theta star, so you don't know the true total variation, but you think that it's reasonable enough. So the total variation won't be very big, or it's reasonable enough in the sense it's well approximated by a piecewise constant function. So you must have some idea of the function, and then you use a method. So yeah. So that's kind of the motivating question I started out with. I was working on just showing these kind of error bounds for Fuse lasso. So then kind of natural to think that, okay, can I design a single cross-validated version of Fuse lasso which and prove that it attains both these types? So you see that you need to choose tuning parameter differently, right? But it would be nice to have a single method which kind of attains both of these in the sense that if the truth is like piecewise constant, you get the faster rate, otherwise get the slower rate. So then this kind of question you can ask for other kind of methods as well. So one question. So this is the motivating question for this work. And so now let me go and try to describe the proposed CV framework. So just to remind ourselves, cross-validation, here are basic ingredients for cross-validation scheme. So you have a given family of estimators, theta of lambda, where lambda is a tuning parameter, like Fuse lasso. Given family, so you want to choose one of them from data, right? So what you have to do, these are the ingredients, you have to decide the number of folds, and then construct, so you decide, okay, number of folds is 2, then you have to construct which data point goes into which fold. So I call them I1, I2, IK. And then somehow the idea of cross-validation. So how do you choose this lambda hat? You kind of estimate the risk for each lambda. The risk or the error, the squared error for theta hat lambda. That's the basic idea. You try to estimate the squared error of theta hat lambda, and you minimize the estimate, these estimated risks, whichever minimizes the estimated risk. That's kind of the empirical risk minimization idea. And cross-validation goes about it by trying to estimate the risk, by trying to construct test data and training data, and estimate the error on the test data. There is no test data here, but you still try to do that. So basically, for any tuning parameter lambda and any fold, what you like or what you have to do is to create a version of the original fact. So let's say Fuse lasso, which is an out-of-sample estimator of theta star on the jth fold. But this should only depend on the data outside the jth fold. Okay, so you have to kind of try to estimate the true signal on a particular fold, but only using data outside that fold. So your particular fold becomes like test data, and this becomes IJ complement becomes your training data. Right? You have to do this for every fold. And you also have to choose a grid of tuning parameters, big, let's call that big lambda. And then once you have created these out-of-sample estimates, you kind of look at the error of these out-of-sample estimates, sum them up, and minimize over this big lambda. So you choose a data-driven tuning parameter lambda in this way. That's kind of the basic scheme. Okay, in any cross-validation sort of implementation. So here is the proposed framework.
So you mentioned the fast rates, right? The fast rate you said achieved when the signal has some special structure.
Like a piecewise constant for Fuse lasso. Yeah.
But Fuse lasso, you'll always be looking at piecewise constant, and that for the fast rates, you'll be only looking at that criterion. Is that correct? You can implement some other structure for which also.
Yeah,
but that's a different thing.
Then you use a different method. Okay. If you think it's piecewise linear, you use a penalty where it's L1 normal second difference.
Nice.
So if you change the method, so depending on
So fast states are always referred to one particular kind of structure.
fast state for fused so fast states are going to be are true. They hold when the signal is piecewise constant.
Okay.
So in many situations, piecewise constant signal is reasonable with not too many pieces. So then you can use fused lasso. Okay, so coming back to this proposed framework. So let me just be a little more formal about it. So first step is you choose the number of folds. So for this talk, number of folds is 2, let us say. So typically either you choose very low number of folds or like very high, or n, number of folds equals n, which is leave one out cross validation. Otherwise you choose like number of folds to be 2, 3, 4. So just set the number of folds to be 2 for us. And then you have to create these folds, I1, I2. And so our framework allows both random as well as deterministic ways of choosing I1, I2. Typically, we might be used to random sort of folds. That's probably more typical in random design problems, but this is kind of a fixed design or signal processing problem. So sometimes deterministic folds are natural. So I'll talk about that next. Okay, so then for each j and each choice of a tuning parameter, as I was saying, you have to construct this outer sample estimate of theta star on the jth fold. So we denote this outer sample estimated by theta hat lambda comma ij complement. Just to remind ourselves, it's a function of y of ij complement, function of the data outside the jth fold, and this lives in R to the mod ij. So the size of the jth fold. So and how you do this exactly is problem specific. So for any concrete problem, you have to choose a way of doing this. So I'll describe when I describe some concrete estimators, like fused lasso and others. I'll describe what I did for this step. But this I'm describing the framework generally. Okay. So in the third step, you choose the lambda hat. As I was saying, you kind of look at the distance of y on the jth fold to your outer sample estimator. So this is basically you can think of this as predicting y as well. So this is prediction error, squared prediction error, sum over all folds. That's the total prediction error, and then you minimize. You choose the lambda hat, which minimizes this over your grid of big lambda. All right. So this is where this is a typical CV framework, and this is kind of your final lambda hat. So your final estimator becomes theta hat of lambda hat. All right. If you go back to the original family of estimator, this is based on the full data. You just plug in this one. This is your final choice. That's what is done, for example, in standard R packages like generalized lasso and CV.trend filter, which implements trend filtering, which is a 1D. Fused lasso is an example of a trend filtering. Yeah, it's one instance of trend filtering. So yeah, these R packages actually just kind of use this way to choose the final lambda hat. But I kind of wrote this as lambda hat int. I mean intermediate. So there's one more step that I will kind of add to this, and then I will be able to analyze it. Okay, so that's purely for theoretical reasons. So this is the final step. But before that, let me just set up one notation. It will be helpful for me to describe things later on. So these outer sample versions, theta hat lambda ij complement, they live in R to the mod ij. They live on the jth fold. So let me just make a notation. Theta hat OOS just stands for outer sample. So theta hat OOS comma lambda. This is an n-dimensional sort of vector which is created by gluing together these outer sample estimates. So like do I have a chalk here? Yeah. Oh. So I guess I'm not saying anything fancy. So
we can push the red button.
Oh, okay. So yeah, basically, yeah. So if the folds are, let's say, deterministic, and the even indices and the odd indices are the folds, let's say, then I have an estimate of theta star on these even odd indices first. So those are theta hat lambda I2. Right? Okay, so whatever they are, and the even indices, I have theta hat lambda I1. So I just kind of glue them together, so then I get the full theta hat lambda OS. Okay, so when I say glue them together, I mean just place them in their rightful order. So, okay, so that's the definition. So this is now an n-dimensional sort of vector. You can think of this is based on the full data again. Theta hat OS, right? Because but its pieces are kind of determined. Each piece is kind of a function of not the full data, but yeah.
Yeah. So the theta hat also depends on the dimension. Theta also depends upon how many. Because theta hat is not a parameter; it's non-parametric. It's the length is the same as the length of y. So
You mean this theta hat OS?
The full thing. So when I do cross validation, I am looking at a particular code. So that what is the dimension of theta? Is the dimension of the size of the code or the complement?
Yeah, so I guess it's this one I'm defining it to be this one will have the size will be the size of the fold, because this is trying to estimate on that fold using data outside the fold. So this is size of the fold, J fold.
Yeah.
So now if I glue them together, I'm just this is just notation, okay? Theta hat OS. So
on the right hand side, that is the optimal thing.
No, this is for each lambda. For each lambda, I can glue them together. So for each lambda, I have these outer sample estimates.
Oh, okay.
Right. So right now I'm not. Yeah. So this theta hat OS comma lambda, you can think of this as a out of sample version of, let's say, if you are in the fused lasso problem, this is an out of sample version of fused lasso. You have to somehow create this. How to create this? I'll describe it. Okay. And now again, so I'm just rewriting this display lambda hat intermediate. So with our new notation, I can just write it as this is just argument of this. There's no sum because the sum is now inside this epsilon. Because these are n-dimensional vectors, right? So I'm just writing it so that I can view this. I'll claim that I'll view this as least squared. So this is just there's a least squared step here that's happening. Okay, so now I'll actually do one more least squared step. So this is my lambda hat intermediate. And I have, so now consider theta hat out of sample with the optimized lambda hat intermediate plugged in, right? So this is kind of my intermediate estimator. And now my final estimator will be obtained by, again, you look at the original family of estimator, which is based on the full data. That's your original fused lasso, let's say, based on the full data. And you choose the lambda that minimizes the distance to this intermediate estimator. So this is a kind of a extra step that I had to add for theoretical reasons. Okay, so there's an extra least squared step. There's not just one. But okay, so this is my final lambda hat, and so my final estimator is theta hat of lambda hat. That's the thing.
So like this is proper learning, or so that's because of course that OS thing is not in the same family.
This is not in the same family, exactly. Yeah, that's exactly true. So yeah, just you can think of it as making it proper. Okay, so let me describe the main result. If you follow this framework, okay, there are how exactly to follow the framework. Of course, there's a question, but if you follow this framework, then you will get a guarantee on the squared error of the final estimator, and the guarantee is basically this. It's a sum of three terms. So the first term is basically the error of the optimal, ideally tuned estimator in your original family. This has to be there, right? Because this is kind of the best you can attain. The third term is a logarithmic term on the grid size, square root log. And the second term is basically the extra thing that comes out. And this is saying that you also have to bound the error of the ideally tuned out of sample version. Okay, the error of the ideally tuned out of sample version. So not only you have to bound this, and this I was claiming. So let me just okay. So I've written down some remarks about this theorem. So the first term basically is available in the literature, as I was trying to say. Like for fused lasso, I told you some results, right? They are exactly, I mean, it's min over lambda. You get a bound on this, right? So But this is where the new part is, because you have to construct this out of sample version and prove. So that our goal could be that prove a bound which on this term, which scales of the same order as this term. Then you can say that, okay, if you do cross validation, your error is of the same order. So that's what we were able to do for a few estimators. Okay, so we were able to show that this term scales like this term up to a log factor, let's say, basically. All right, so let me say some things about this result. So this theorem that I showed you can be thought of as a general wrapper around any family of estimators. You can kind of think of this as a general wrapper, and I talked about these three terms. So now there are two questions. The two questions are how to construct an out-of-sample version, right, of, let's say, fused lasso, and the answer is there are multiple ways, and I'll discuss three approaches in a bit. And then once you create this out-of-sample version, how do you prove a bound for an ideally tuned out-of-sample version? And here, you may have to do some sizable analysis, which is comparable to the, in fact, more difficult than the original problem, because here there's an out-of-sample element as well, right? So depending on how you construct it, you might need to do a sizable analysis, and you can use ideas in the literature which kind of bounds the first term. You can use these ideas, but there's an extra part, which is this out-of-sample part, which you have to deal with somehow. So in fact, it's a harder problem than this. But so there's this extra step that you have to take care of as well. So if you want to apply this framework to any concrete estimator, you kind of might have to do an analysis case by case on a case by case basis. Good point. Although I'll describe an approach where you don't even have to do the analysis, but it may not be the best approach. So I'll come to that. So let me describe some of the proof ideas behind this main theorem. This won't be long. This is actually easy enough that I can try, at least give a sketch of the main result. The main sort of technical part is technical part will be to bound the second term. All right, in this that sort of takes most of the space in the paper. But let me just try to, I think, because this way of presenting a guarantee on the cross-validated version is nice. And so let me just try to explain the proof idea behind this result. So the main kind of point is, or insight is, that you want to view this lambda hat intermediate. Recall this lambda hat intermediate. I was saying this is a least squares way to choose the lambda hat intermediate. So what I mean is exactly this, that you can view theta hat out of sample lambda hat intermediate as a least squares estimator, and least squares estimator over the set of all possible out of sample estimators, right, where lambda belongs to big lambda, right? So that's so you want to use least squares theory basically. So, but before doing least squares theory, so you can do least squares theory maybe to analyze this out of sample version, but you want to analyze the final one, not the out of sample version, right? So that's precisely why I had to do this last step, as Piyush was saying. So you have to kind of make it proper, and because of this last step, you can get a basic sort of inequality which says that the error of the final estimator is bounded by twice the error of the optimized out of sample estimator plus this the best possible error of the ideally tuned particular estimator. So this term already is basically the first term in the bound, right? So now I'm left with, what am I left with? I'm left with just analyzing the intermediate estimate, right? So this connecting this to this is needed, and for that only the last step is needed. That's all I'm claiming, and this is not hard to prove at all. In fact, this is just 2 lines. Just use the definition of lambda hat and a couple of triangle inequalities. So that's not hard. Okay, the second step is now I have to analyze this, and as I was saying, I want to do this as a least squares estimator over this bunch of estimators themselves. So I'll basically use a Oracle inequality for finite least squares. The grid big lambda is going to be finite. It's a finite number of choices of the tuned parameter. that I'm going to choose. How I choose the big lambda, I'll also mention at the very end. So I'll use an Oracle inequality. The problem is that there's one thing that you have to be careful about. This is the least squares over a random set. Because these are themselves estimated, right? Out of sample comma lambda. For each lambda, they are estimated themselves. So typically results for least squares are stated for deterministic parameter spaces. But this is a random parameter space. So here is the Oracle inequality. So it's kind of the way it's proved is also similar to the way you prove this for a deterministic parameter space, except that you have to stop at some point before. So, but anyway, so here is the Oracle inequality that I'm claiming, and this holds for even when big theta, this parameter space is random. Okay, so the first term is basically again a distance term of your parameter space to the truth. This is generally stated, so Y again follows a Sabyasachi sequence model. And the second term is a maxima term, maxima of these normalized inner products. Okay, so this is a pointwise inequality. Okay, so there's nothing random about it. This is a deterministic kind of inequality. All right, where big theta is also random. So if big theta was deterministic, then this is easy to bound because this is IID subgaussian, and these are unit vectors. So if you have finitely many unit vectors that you take max of inner products themselves are going to be subgaussian sigma. If epsilon is subgaussian sigma, each entry, and this is a normalized vector. So then you have finite maxima of subgaussian sigma random variables, and that's a standard result. It's square root log of the number of such random variables, right? That's what you see typically. But since we don't have a deterministic one, you have to kind of stop this proof a bit early and also do a few more things. But anyway, that's kind of the Oracle inequality we'll use. And now, okay, now we can use this. The point is for us, because the number of folds is small, I'm considering the number of folds to be small. I claim that I can still get a square root log cardinality bound here. What's the cardinal? Big theta's cardinality is big theta is that guy over for me. So the cardinality is just the cardinality of big lambda. Okay, so so this maximization can be done by just observing. So you can first write the inner product as a sum over all folds, inner products, right? And take the max inside, so it will be even bigger. Okay, and now you can also instead of this normalization, you can put the smaller normalization so that it becomes still correct. So the dimensions are smaller for these vectors. But now observe that this vector theta hat out of sample lambda ij is a function of the data outside the jth fold, right? It's a function of y ij complement, and this is epsilon ij. So this is really a function of epsilon ij complement. This is a function of epsilon ij. So they are independent. So to be technically correct, the folds are also random. So you first condition on the folds, okay, and then you condition on epsilon ij complement, or the data outside the jth fold. Then only this thing becomes random or remains random. But the conditional distribution is the same as the conditional one because of independence. So this is again a finite maxima of Gaussian sigmas. Okay, and finite with cardinality log mod lambda. And so conditionally that's true, and this root log mod lambda term doesn't depend on what are the precise vectors that you're taking this inner product with. It's just the number that matters. So therefore here unconditionally also this will be true. Okay, that's kind of the main point. If there are questions, you can ask. That's kind of the main point. So you kind of condition on the folds and the data outside the jth fold, then see this as a finite maxima, and you can then argue this is also going to hold unconditional. Okay, so all right. So now let's.
That's because the norms of the vectors are.
Norms are, yes, exactly. These are norm one. So if you have norm one,
then
yeah, exactly. Okay, so now let's try to apply this framework to some concrete estimators. And here I'll be focusing on some method, just a methodological aspect. We'll not sort of go into how to bound this error of the out of sample one, but just how to create this out of sample one. Right? And what I will do is I'll basically describe 3 estimators, which I looked at, and 3 different kind of ways of coming up with these out of sample versions. They will be quite natural, hopefully, or intuitive. So to apply our main result, the main task is to design this out of sample estimator. And you can think of this as basically a noisy completion problem. Instead of just trying to estimate the the fold which is outside, just try to think of a problem where you want to estimate the entire vector, but you only get data from some portion, like id complement, outside the JS fold. So essentially, these are similar problems. So you can just think of it as a completion problem, because that term might be more familiar to you. It's just a noisy completion problem now that we have faced it. So the same kind of problem where you have the same structure, you may be targeting piecewise constant signals. So you have to design a completion version of fused lasso, let's say. Right, that's the problem, and then prove a bound. Not going to too much how to prove these bounds. But yeah, so now I'll go through. So first, fused lasso. So we know what is fused lasso. So in this case, what we did is we just created 2 folds, and the folds are very simple, just even indices and odd indices. Okay, so just even indices and odd indices. And how do I create a completion version? Maybe I want to create a completion version with only a function of the even indices, data on the even indices. So I'll create a new data vector, let's call it y tilde, which is just going to be equal to y on the even indices. But on the odd indices, I'm going to interpolate. And I'm just taking the simplest possible interpolation scheme, which is just take the value to the right. You could have also taken averages of the 2 ones on the 2 neighbors. Is that clear? So I'm just interpolating and creating this y tilde. And now feeding y tilde in my fused lasso objective. This is the fused lasso objective. I just sort of interpolate, create this new data y tilde, and that's what I define to be my completion version. So now I go back to the old notation because I'm going back to the old, but these are now n dimensions. This is a completion problem where you observe only data on ig complement, let's say. So yeah, this is the strategy, general strategy. You kind of, whatever you see, you keep, and you interpolate in the middle, and then you feed that vector into the optimization objective. And so I call this, let's call this approach interpolate then optimize. Okay. That's a pretty natural way to maybe generate these sample estimators. So in the paper, we then have to prove something about fused lasso, this fused lasso. Right? We just see the even indices, and this is the way you interpolate. But yeah, things work out. Now let me take a little bit of a detour and describe another estimator. This is the matrix or image denoising method, which I have worked on, and it's called Dyadic CART. So this was proposed by David Donohoe in a 1997 paper. So to describe this estimator, I'll just take a few slides to describe this estimator. This is a detour, then we'll come back to cross-validation. So to describe this estimator, I need to describe what are recursive dyadic partitions of a n by n grid. So I'm in a image denoising setting or a matrix denoising setting. So I have a, let's say, n by n grid, whatever. So recursive dyadic, an example of a recursive dyadic partition is you have to split at the midpoint in either coordinate, x-axis or y-axis. Maybe this is how you do it. Then you have 2 rectangles. Maybe this one, here you will still do this, maybe this, something like this. This is the recursive dyadic partition. And every time you're splitting at the midpoint of one of the coordinates. Okay, so there's a, so that's a recursive dyadic partition. And now you can consider the set of all possible recursive dyadic partitions of an n cross n grid. That's a finite set because the grid is finite, right? So now you can consider an optimization problem over the space of all such recursive dyadic partitions. They're quite a good set, but you consider this optimization problem is again sum of 2 terms. There's this fitting term, which is y your data matrix minus p pi y is just the, in each rectangle of this partition, you fit the mean of the y on that rectangle. Okay, so it's that's p pi y. So you look at this squared distance term, and the penalty term will scale directly proportional to the number of rectangles because in Dyadic partition. So this is a finite or a combinatorial optimization problem, right? That's how you get the optimal partition, and the final estimator is just your p pi hat of y. Okay. So this looks complicated in the sense you have to solve this big problem, where is it even computable? But the point is, this is actually computable. And this is not only computable, it's computable very fast in linear time. That was shown by Donovan in this paper. It's a very elegant kind of method where the algorithm, it's a very beautiful dynamic programming algorithm and so on. You can also write Dyadic CART equivalently as the squared distance plus a penalty term, but the penalty, I'm defining it to be, this complexity parameter is k RDP of theta. For any matrix, this is a number, this equals the cardinality of the minimal recursive Dyadic partition of n cross n, such that theta is piecewise constant of the partition. So you can also write it this way. I just wrote it this way so that in the next slide I'll use it. So this method, I, along with Shubhajit Goswami, who is in math here, so we kind of worked on this method and looked at it statistically and showed it has some very light properties. So if the true signal has k number of pieces, if the true signal is also piecewise constant with k pieces, it will get a k over sample size mean square error. And this k it adapts to k basically. It does not know the true signal is k, of course. So whatever the k is, if it's very simple, it will get fast rates. If it's more complex, it will get slow rates. So it has a nice adaptive property. Anyway, these are some pictures of what you can get by using Dyadic CART. So that's the fit. That's the original signal. And for a circle, you need more rectangles.
So you're creating all these rectangles, and in each rectangle you're doing some least square effect or something, or
no. So so I'm basically computing this optimal partition. So given a matrix, this is the optimization problem I was talking about. So you have this space of all recursive Dyadic partitions. It is quite a big set, but you can compute this, is what I was claiming. So this is basically, by tuning lambda, you will get different fits. So
within each partition you have some data y, and
you have a data y, which is a matrix or image.
But also within the partition you have some kind of some part of the data. And then you have some P of the partition y, which is the mean thing that you have there.
Yes. So let's do a small example. So if my matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 by 3, and let's take a particular pi, recursive Dyadic pi. So maybe this case, maybe this one. So then p pi of y is just replace these by the mean. So this will be 3 by 2, so 3 by 2, 3 by 2, and so on. Right? 6, 15 by 2, 15 by 2, and so it will be a piecewise constant matrix. So for each partition, p pi y is also a matrix. So you look at the distance squared. So this is, if you use that partition to estimate or kind of y, then that's kind of the fit equals. And but you don't want to use too many rectangles. So this is a global kind of regression tree method, essentially. Okay, but the regression tree family is just a recursive Dyadic.
Somehow it's very fast to solve this problem.
Yeah, there's a dynamic.
What's the intuition? How does that work? How do you solve it? Is there some greedy kind of way of it?
It's not greedy, but it's a dynamic programming. So there's some nested structure that you can use. I don't know if I can explain more better, but it's very simple. It's not very complicated.
I see.
But yeah.
So I didn't have this penalizing term, then you just make the.
Then you just choose the finest partition. The p pi y will be y. That's of no use. You want to choose a smaller, like a coarse enough partition.
And now your optimal solution is a function of lambda. So,
exactly. So here I did cross validation and chose the lambda. That's what.
And somehow again there's some localization structure. So when I move lambda, my grids are kind of increasing, but in a nice way.
Yes. So if you choose lambda very high, it will just fit a constant image.
Right.
If you choose lambda infinity, let's say. But if you choose lambda 0, it will be y. So in between, there's a nice choice.
But in a continuous way, can I measure the data? Maybe something like that.
Not
Technically,
not continuous, but yeah. Okay, so how do I? So I guess there's no cross-validated version of Dyadic CART which has been studied. So what we did is here we just took random folds. Again, the number of folds is 2. Each pixel, probability half, goes in fold 1 or fold 2, independently of all other pixels. And how do I define my completion estimator? So again, remember, completion estimator means I observe a part of the data. I have to design a version of Dyadic CART by just observing a part of the data. So ij complement is the part of the data outside the jth fold. So I just, if I go back to the earlier definition, equation 1, in equation 1, I just replace y with whatever I've seen. I have not seen y, but I have seen yij complement. So in the optimization itself, I just replace yij complement and theta ij complement. So now, of course, well, even initially the solution may not be unique in this problem, but here, of course, it's also not going to be unique. It's not strongly convex anymore because few quadrants are missing in the square distance stuff. But you can take any one of them. Let's say.
So this complexity is for exactly solving this optimization problem. Or
Exactly. Yeah, that's the I was also very.
Sorry, just to simplify first. So you're saying that, okay, I'm given all this data, I'll create some kind of fold, but I'll keep some data, I'll approximate some other data.
I'll choose a random fold.
Yeah.
I'll create 2 folds randomly.
Yeah.
And then I'll try to solve this optimization problem. Again, this is also computable, which I showed in the paper. Yeah.
For each fold, you'll solve the problem first.
Yes.
And then what do you do?
So once I have this completion version, or the outer sample, I mean,
so is it n squared or n squared log?
it's n squared actually. So yeah, you remember this framework, right? So once I have the completion version, I also have these out of sample versions because I'll just use them to predict on the outside this fold, right? Then I'll follow this process. I'll choose the lambda hat, then I'll lambda intermediate, and then I'll do this to get my final lambda hat. So that's the original process that I was talking. I mean, the original cross validation implementation I was talking about. Okay. Yeah. So again, you see that this principle of coming up with a completion estimator is also quite generalizing. I could have used it for fuse lasso. Created these 2 folds and just used inside the fuse lasso objective. I could have used yij complement. So I call this approach restrict then optimize. So you restrict your indices to your indices where you have which you have seen, and then you optimize, right? Instead of interpolating. So this is these 2 ways might be very close solutions also. Actually, that's what turns out to be true because all of them are going to be close to theta star. The sample size is large enough. So yeah, so why I did this approach for Dyadic CART and that one for fuse lasso is for technical reasons. But my point is these 2 approaches are pretty intuitive and you can do them for pretty much any estimator. And here is my last example. So consider a standard matrix denoising algorithm, which is the singular value threshold. Right? So which is basically you want to denoise a matrix, so you observe a noisy version. So that's why you take the FBD of y, and then you basically just take some closest rank approximation of y, or you kill off the singular values which are smaller than some threshold lambda. So lambda is the tuning parameter for this method. And in this subgaussian sequence model, theoretically prescribed value is this. It's 2.1 sigma root n. Sigma is the noise standard deviation, which is unknown. And 2.1 is, anything above 2 is asymptotically okay. But even this, even if you know sigma, the 2.1 might be problematic when sample size is small and so on. Of course, you don't know sigma. So again, you kind of try out various thresholds in practice, right? So again, kind of do cross-validation in some sense. And okay, so here I kind of want to describe another approach to do completion, so which I used in my paper. So what I did is, again, it's, so I created Y tilde, which is a new data matrix. Okay, there's an old data matrix. I have to create a completion version. So that means it should only depend on one fold, right? So what I do is I create Y tilde, which is 0 outside that fold, and double the entries on the fold that ij complement, let's say. So it's doubling on one fold and zeroing out on the other, right? That's Y tilde. And now you just apply your SVD to Y tilde. Okay, so Y tilde becomes a function of ij complement, right? Because I've doubled the entries in ij complement, I've zeroed out the entries in ij. Right. So again, this might sound why should I do this? But this is, yeah, I'll explain in a bit. But if you do this and then follow the procedure that I was mentioning, this cross-validation framework, so choosing lambda hat, then we showed that this CV SVT estimator also adapts to the rank of the underlying two matrix. So it's known that if you choose the tuning parameter properly, of course you get this Rn by n square mean squared error, where R is the rank. So you adapt to the rank basically. So here also that property is still true for this entire approach, entire method. And we call this approach of creating completion version as zero doubling. So this is again nothing fancy, it's very easy. So all I'm saying is, so for each entry, so each entry, let's say each pixel, it's going to be with probability half double and with probability half zero double. This is because the folds are chosen randomly, right? So when you do that to a random variable, say x is the random variable, and theta star is its mean. So when you so when you double this, so when you create this operation where it's 2x with probability half and 0 with probability half, you get a new random variable x tilde. Right? So x tilde has the same mean. It will have the same mean, and not only that, it will have this if it was originally sub-Gaussian around its mean to begin with, it will still be sub-Gaussian around its mean, except that there will be a mean term also in the standard deviation. So what will this imply is that this new zero double matrix Y tilde will itself also be sub-Gaussian with the same mean theta star, but with a potentially increased variance, which is theta star infinity. So essentially what this means is if I zero double and then apply my method, essentially I'm in the same model with increased variance. So to bound, and remember, bounding this out of sample version or the completion version is my main task if I use this framework. But now the completion version is just the original family applied to Y tilde. Y tilde is in the sub-Gaussian sequence world, so I can use existing results. Basically, I can use the existing results just like that. Once I have this observation. So this means our framework plus the zero doubling way of creating completion version is give the complete theoretical wrapper. You don't need to do a separate analysis. And I could have done the zero doubling for fuse lasso or the other methods too. So, but why am I using zero doubling here and not there? It's because it's not clear practically which one is the best. Practically, I gave you these three kind of ways of creating completion versions. For some versions we experimented, we saw zero doubling could be a little worse, maybe 1.5 times worse, depending on, because there is theta star infinity, right, which you also don't know. Typically, problems, this is like big O1. So you're fine, maybe up to some constant factor. So, but you might want to analyze the other versions of completion because they are practically performing better. So I'm not sure which one is better, or even if there's an answer to this, because in different problems, the different one might be better. I don't know. So yeah, there are these three kind of approaches. One is interpolated optimized, one is restricted optimized, other is zero doubling. There might be others. And it might be interesting to obtain such a general result for the restricted optimized. That might be one most natural one. It's for the zero doubling, which increases the variance visibly. Anyway, so let me just finish. One comment on practical performance. So we did more sort of simulations with in different scenarios. What we saw is that when we compare it to like if there were R packages, or we compare it to the if I stop at this lambda hat intermediate, use that one, compared with other model selection methods. All of them we were pretty competitive. So it's not that we suffered a lot. We are not beating anybody, but we kind of are competitive with this one. But this one is harder to analyze. I mean, it stops at the intermediate lambda hat, and also the folds are chosen slightly differently. So but for this, of course, it somehow practically is also not very bad. And let me say something about how to choose this big lambda, this grid. So you want this to be sparse because computational complexity depends linearly on this, right? To solve that many potentially complicated optimization problems. So you want this to be sparse, but on the other hand, you want this to be fine because you don't want to miss the right value. The right value is something. But here there's a fact. The fact is that the error bounds are going to be directly proportional to lambda in these problems, which means that if you miss the optimal lambda by a factor of 2, you pay a factor of 2 at most. Okay, so and you can kind of in the scale, the problem scaling that I wrote, the optimal choice of lambda is always smaller of it. It will diverge, but it's going to diverge slower than n. So essentially, you have to cover the range, let's say 1 to n. And I do that in a geometrically increasing way. That's the simplest thing to do, so that it's sparse. There's only like log in many choices. So the computation is quite reasonable. And I mean, theoretically, you miss by a factor of 2. Okay, so to summarize, what I said is I kind of tried to present a general and theoretically tractable framework for CV in the signal denoising setup, and we suggested 3 different approaches of coming up with a completion version, which is necessary in this framework. And in the paper, we kind of analyzed CV versions of these estimators. For each one of them, we had to do a separate analysis. Except the SBT, where the analysis was easiest because we used the zero doubling method. We could have used others, but anyway. And the main point I want to say is that this idea should be extendable to other kind of settings. If you want to, if you want to look at other losses instead of square loss, should be extendable. If you want to address heavy tails, then you have to replace the square loss with something like N1 loss. But more interestingly, if you might also want to analyze the deep one-out version, which sometimes performs better in practice. But of course, that's computationally more expensive because you have to solve the optimization problem many times. But for leave one out, this kind of separation into folds, when I was talking about the analysis of the main theorem, you have to handle the folds really. So some new ideas needed to analyze the leave one out. You cannot use what we observed. So what we observed holds, is valid for a small number of folds. So with that, I stop and I keep moving ahead.
So what was the parametric thing? Like, so if you're doing, say, SVM or something, the number of parameters is very small. And so there also, you will often just use cross validation over the parameters. But the thing is that, so the only difference I can see that there's no, so like you learn the classifier, so there's no, you don't have to actually construct some amount of sample thing, especially because the classifier is supposed to work everywhere anyway. Is there a simplify things or?
So that's typically analyzed in the random design setting, right? The classification XI, YI, ID. Yeah, I mean, even in that setting, you have to create. You have to create somehow a version of SVM which acts on only a part of the data and test it.
Yeah,
So you do that.
You do that, but then
Yeah.
that so it's already proper in some sense. Like so this so here was the one difference the actual algorithm and because this is non-parametric. But here the means so there this step is not there. Like you just run an SVM on the Tractable. It gives you the classifier, but the classifier doesn't know how many.
You have to run it on
small
sample
except something. But you get the parameters. And so then you have a function like the what.
but you have to choose the right parameter, right? So how will you have to create test and failure actually. Yeah, you have to choose one.
Yeah, yes, so it's the same setup, but because this is a thing that you are predicting, just some number of some parameters. And once you have the parameters, the function can be applied to any dimension. So here the difference was that this theta star or
Here the difference was that it was not in the original family theta hat lambda. It had OOS, which are doing least squares on. In the SVM, would it be?
If the OS thing seems to be like it's not needed.
It's not needed. Okay.
So
then maybe we can do away with the last step. So yeah. Because the last step is needed, as I was saying, just to relate the final one to the.
But I guess even then, when we need a little bit of fine tuning for the rest of it, right? It doesn't work directly, but does it work directly?
Yeah, I don't know.
Yeah, I mean, so I don't know if the auto sample is exactly would be in the family, but if it is, then you can stop at lambda hat intermediate. That take that one, and then the analysis will still hold. Because the analysis was for the second, this auto sample version, using this breaking into folds. So that's you exploit the independence within each fold. So that's a very simple observation, but yeah, that's the number of folds is small, it should hold.
Because I guess in these other kinds of algorithms, which people use like gradient descent, they are hyperparametric people try to set like learning. And then lambda also there, regularization extent, robot extent.
Sure, you can you can use this framework, but you need to prove those things for gradient descent, these ideally tuned bounds and so on. But once you prove them, you can use this framework on top of it. All right.
Stop the